We've seen that exactness is a very useful concept in algebraic topology. So a natural question is, if I have an exact sequence, say of R modules, and I apply a functor to it, say to abelian groups, do I preserve exactness? And this is the question we want to ponder in this video. So correspondingly, we make the following definition. A, say, covariant functor F from, and now we're always dealing with modules over non-commutative rings, so I should say from left or right R modules. To the category of abelian groups. Is called, and now we distinguish two cases. It's called left exact if for every short exact sequence, whoops, I want this to be black. If for every short exact sequence of R modules so for every short exact sequence of left or right R modules, call it 0, M1, M2, M3, and to 0. If I apply now the functor to this short exact sequence, then I only require that the portion of the first four objects here be exact. So if for every such short exact sequence, the sequence zero f of M1, f of M2, f of M3. And now I finish. This one is exact. And then you can already guess what the definition of right exact is. Namely, if, and then as above, for every short exact sequence of this kind, the sequence, and now I start at f of M1 and I end at 0. fm2, fm3, 0 is exact. Okay, so this is our definition for covariant functors, so if you want for ordinary functors, and we should also give a contravariant version of it, and that goes as follows. So in this case, the best way to memorize it is we define now left exact as before, but we reverse the arrows, so meaning for a short exact sequence which now goes the other way, so M1, M2, M3, 0 with arrows pointing to the left, and now left exact still means that the 0 is left on the left hand side, so this sequence here. Now contravariant functor means the arrows are reversed, so we obtain such a sequence here. This sequence here is exact. And I just put 3 dots here because now I think you can add the definition of right exact for contravariant functors. This is now clear. And the two functors which were of interest last time were the Tensor-functor and the Hom-functor on R modules. And the question is which of them is maybe left and which of them is right exact, and this is answered by the following proposition. So if we have a left R module M, then actually it turns out that the Hom-functor is left exact and the Tensor-functor is right exact. So then Hom are m blank. So in this way, it's a covariant functor, and this is left exact in the above sense. Whoops. And the tensor-functor, blank tensor R m, is right exact. Yeah, so one cannot expect in full generality that those functors preserve short exact sequences, but depending on whether it's the Hom or the tensor functor, it preserves the first four or the last four terms of a short exact sequence, or the exactness of the first and last four terms. And the proof now uses the tensor-Hom adjunction we proved last time. Namely, there is a nice observation. So the statement that this here is an exact sequence, 0, m1, m2, m3, so this one is exact. This can be equivalently stated as saying that I have a pullback square, which goes like this. Make me the autocorrect, yes. m1, m2, m3. Yeah, so this portion of the diagram is just this portion here. And here I go to 0, and then I go to here. And if this square here is actually a pullback square, then this means exactly the same thing as if this sequence here was exact. So let's convince ourselves about this. I mean, what does this mean, that this is an exact sequence? Well, it means that I have a homomorphism here from m2 to m3, yeah? And exactness now means that this arrow before here is just the inclusion of the kernel of this homomorphism, yeah? That it is the inclusion, meaning that it is injective. That's the statement that it's exact here, that we have a 0 here, yeah? So this arrow here is injective. And exactness here means, well, the image is the kernel, yeah? So in other words, m1 is the kernel of this homomorphism. So this exact sequence says nothing else than I've got the inclusion of the kernel of a homomorphism. And now if you look at this pullback square here, so the input data of this pullback square is this arrow and this arrow, yeah? So I have the homomorphism m2 to m3, that's the one we had here. And now what's the pullback of this diagram? Well, it's by construction the product of those two, so pairs of elements in m2 and 0, and the requirement is that m2 is mapped to 0 here. Yeah? In other words, it's all the elements in the kernel of this homomorphism, and therefore m1 is just the kernel of this homomorphism here. And this being a pullback square means precisely that m1 is, that this homomorphism here is the inclusion of the right-hand homomorphism. Yeah? So this is really exactly the same thing. Saying this is an exact sequence is the same thing as saying this is a pullback square. And now you can already guess what happens. We have a dual statement to this, namely if m1, m2, m3 to 0 is exact, oops. Then dually, this is equivalent to saying that this square here is a push-out square. So m1, m2, m3, and 0 here. And this is a push-out square. So let's ponder why this is true. So what does exactness of this sequence mean here? Well, consider the homomorphism from m2 to m3. This is a surjective homomorphism by the 0 here. Yeah, so this is a surjective homomorphism. And then this Noether isomorphism theorem says that M3 is actually isomorphic to M2 modulo the kernel of this homomorphism. But by exactness here, the kernel of this homomorphism here is the image of this homomorphism. In other words, M3 is M2 modulo the image of this one, and that's precisely the co-kernel, yeah? The co-kernel of this map here. Yeah? M2 modulo the image of this map is the co-kernel of this homomorphism here. And on the right-hand side, if I consider this push-out square, then I have this homomorphism m1, m2, and going here to 0. So what's the push-out? The push-out means I get the direct sum of these two and I have to mod out the relation that everything that maps from M1 to here should be the same as if it had mapped it this way around, which means it is 0. In other words, it's just the coproduct of M2 and 0, which is just M2, modulo the relation that everything that lies in the image of this homomorphism is 0. And this is precisely saying it's the co-kernel. Yeah? So the push out of this diagram is the co-kernel of this homomorphism. The pullback of this diagram here, that's, so the pullback is this object here, that's the kernel of this homomorphism. Yeah? These are the two dual statements which translate the exactness of these two exact sequences. By the last video, we also spelled out the Hom-set adjunction, and we saw that the tensor product occurred on the left-hand side in the left variable and the Hom-functor on the right-hand side in the right variable, meaning tensor is left adjoint and Hom is right adjoint. So let's put that down. Hom R M blank is right adjoint. And blank tensor M is left adjoint. And now our previous work is useful, namely in the first part of this course, Algebraic Topology 1. Exercise 7.1. So exercise sheet 7, number 1. There you proved actually that right adjoint functors preserve limits and left adjoint functors preserve colimits. So let me write this down. Right adjoints preserve limits and left adjoints preserve colimits.
So on YouTube, it's the topology course.
It's on YouTube, it's the topology course, yes. But again, it's on the exercise sheet, right? It wasn't in the video. And left adjoint preserve colimits. Okay, so maybe a way to memorize this is that, well, left adjoints are determined by homomorphisms on the object, yeah? On the object going to another one, which is the same thing for those co-cones here, for the colimits. So therefore, left adjoints preserve colimits and the other way around, yeah? Right adjoints are determined by homomorphism into the object, and therefore limits is the correct thing they preserve, because limits also go into the diagram. So what does this help us now in our situation? Well, the pullback here is a limit. Yeah? This M1 is the universal cone on this diagram. So this one is preserved this limit is preserved if I apply a right adjoint functor and the Hom-functor is right adjoint. So meaning if I apply Hom to this square here, I get again a pullback square. And that means by this equivalence that 0 Hom is exact. And dually down here, so the push out here, that is an example of a colimit. So this M3 is the universal co-cone on this diagram. So this is preserved by left adjoints. And the tensor product is an example of a left adjoint functor. So if I apply tensor product to this square here, I get a push out diagram of tensor products, where this equivalence is the same as saying that tensor to 0 is exact. Yeah? So this is a general nonsense proof showing that Hom is right exact and tensor is left exact. I'm not sure if I said it correctly now. I think I said Hom is right exact, which is wrong. So the confusion stems back from one thing here. Right adjoint functors then become left exact. Yeah. So apologies.
Say it once more. Yeah.
So apologies. The correct statement is the Hom-functor is left exact because it is a right adjoint, and the tensor product is right exact because it is a left adjoint. Okay. Yeah. So there's hardly any way to memorize this other than be confused, think about it for a long time, and then get it wrong. Yeah. Anyhow, so the question is now, if we make some assumption of on our module M, then maybe we can do better. Yeah. So the Hom-functor is left exact. So maybe if the module M satisfies a certain property, it might be exact altogether. And this is actually our next proposition. The Hom-functor turns out to be exact if and only if M is a projective module.
It's a good exercise, by the way, to think about this proof also in more concrete terms. So prove that the tensor product is right exact using the construction.
Yes, yeah, you can do it directly, but I thought, why did we do all the work?
No, that's the right proof. I'm just saying that you have to prove that surjectivity is preserved. That's the main point by the tensor product. Mm-hmm. And whenever you have a construction that defines this as a quotient of something, like in the tensor product, surjectivity is actually easy to check. Mm-hmm. The difficult part is injectivity, because dividing out something screws up injectivity. Mm-hmm. It's very vague, and in fact, it is not left exact, so it is not always preserved.
But maybe this is a good way to memorize it, if you have this construction in mind. Yeah, actually. Yeah. What you should maybe memorize is left adjoint being left exact is wrong. Maybe like this one can remember.
Very helpful.
Yeah.
I think you should never remember anyway. So.
Okay.
What's wrong?
Okay. So let's focus. The Hom-functor is with no assumption on M left exact. So claiming that it is exact means we only have to show that it preserves surjectivity under the additional assumption that M is projective. So let's put this down. It's the first observation. Exactness is equivalent to preservation of surjectivity. Yeah, because preserving exactness of the rest of the short exact sequence is automatic, as we just saw from the general nonsense. And let's see why this now holds if and only if the module is projective. So let us give ourselves a surjective homomorphism of R modules. So G from A to B, say, which is double arrow, so which is surjective. Then, I need to consider the induced homomorphism under the Hom-functor. So that's this one. So Hom R M comma A going to Hom R M comma B. And actually, let's recall how the functor even works. So if I've given this morphism G, how do I get a morphism here? Well, I take a homomorphism from M to A and I just compose it with G to get a homomorphism from M to B. So in other words, this map is just given by composition with G. Okay, and now I have to prove that this is actually a surjective homomorphism if and only if M is projective. And to see this, well, let's first of all put it down. If this is surjective, if and only if M is projective, meaning M satisfies a universal property, that's the definition of being projective. And well, this universal property can be stated in terms of such a G, namely if I have a surjective homomorphism from A to B, and I have any homomorphism F from my projective homomorphism, projective module M here, then, or say M is projective, if I can always solve this lifting problem and find an arrow from A to M, which makes this diagram commute. And now this is actually already the solution of the proof. So let's see why this is true. So first of all, let's say we assume M is projective, and we have to see then this one is surjective. So if we have a homomorphism from M to B, call it F, then this actually poses a lifting problem because this homomorphism F goes from M to B. We have got our given surjective homomorphism here. We can extend this diagram and obtain a lift H here. And then actually, well, the commutativity here says precisely that G is equal to, which way around? It says that I'm confused with the direction. Sorry, yeah, the arrow is wrong. Yes, this is why it did not work. So the extension goes in this direction here because I want to solve a lifting problem. Yeah, so the surjective map, sort of this should sit above this. This is why I was confused. So I want to lift this arrow along this surjective map. So the arrow needs to go here. And then again, the argument. So I want to show that assuming I have the solution of the lifting problem, then given an element from here, I find a pre-image here. An element here, F from M to B, gives me a map here, poses this lifting problem, and if M is projective, I get this solution H of the lifting problem. And this solution H now satisfies that F is the composition of G after H. Yeah? So H here, this solution here is the pre-image I want to find for the given F. So then I have the surjectivity. Yeah? So that was the direction. If the module is projective, then this map here is surjective. And now the other way around, well, if this map is surjective, well, it precisely means that every lifting problem has a solution. Yeah? If this is surjective, it means for every F here, which I can put then in this diagram here, I find a pre-image, meaning there exists such a solution. So it's really a reformulation of the universal property that, projectivity means that the Hom-functor is exact.
So far you considered the Hom-functor as a covariant functor. So Hom M was fixed, M was in the first variable. Mm-hmm. But you could also put M into the second variable, mm-hmm. and then you would get a contravariant functor.
Exactly, and then there is a dual.
And then for me, it's always the confusion is even worse about left exact, because then the arrows turn around.
Yes, that's
and
right.
And left gets right.
Okay, so let's introduce the corresponding dual object as Roman suggests. So dually, an R module, and now we just dualize the concept of projectivity. An R module I is called injective. This is supposed to be the dual to projective. It's called injective if, and now I don't have to think, I just take my diagram here and I reverse all arrows, yeah? I mean, I dualize the diagram that, so maybe I can make both visible. Write this. So dualizing means surjective epimorphism goes to monomorphism goes to injective, so it's now a given monomorphism from B to A, and I consider any homomorphism out of B going to M, and then the solution goes into the other direction. Sorry, and M is now I. Yeah, I wanted to call an injective module I. So in words, it means an R module I is called injective if for every fixed injective homomorphism from B to A and every homomorphism from B into my module I find an extension, if you want. Yeah, you should think of B as being included here in A, and I can extend this homomorphism F from B to all of A. Yeah, so this is usually the dual thing to lifting. Yeah, finding a lift is dual to extending a map. Yeah, and this universal property, so that this arrow exists and is unique, this defines injectivity, and it actually turns out what Roman already suggested. The injectivity of a module is equivalent to saying that the other Hom-functor, where the blank is on the left-hand side, this contravariant functor here, is exact. Yeah, but we defined above what left exact and right exact means in the contravariant case, and well, I mean, it just means in this case a short exact sequence by applying
that's exactly what I found. Well, maybe not now anymore, but which I found confusing when I learned this stuff, that the notion of exactness is clear. But the notion of what does it mean left exact if you have a contravariant functor and now arrows get turned around.
Yes, it's confusing, but I do suggest that the best way of memorizing is just the input sequence should be written with reverse arrows, yeah, as we did above here. So you just draw your short exact sequence with reversed arrows. So if you apply the functor, then the arrows get reversed in the usual way. And in that case, left and right exact means what it originally meant. Yeah, left exact means the zero apply.
Yeah, so what you're just saying is, in other terms, you look at what is the Hom-functor? It's a functor from what to what? It's a functor from the category of R modules to abelian groups.
Yes.
And now you're looking at the opposite category of R modules. So whenever you have a category, you can define formally the opposite category by taking the same objects but reversing all the arrows.
So sort of this is an arrow from here to here in the opposite category, if you want.
Right, and then this other Hom-functor where we fix the second variable becomes a covariant functor from the opposite category of R modules to abelian groups. And then we take exactly the same meaning of left exactness that we had before, but maybe we should write it out, spell it out.
From M3 to I. Yeah?
No, I think it helps to see that.
Okay. Excellent. So, yeah, so injectivity is the dual concept to projectivity. Let me just, without proof, give you examples of what you should think about. So, Q and also Q mod Z as Z modules are are injective modules. And to give you non-examples, well, just Z over Z is not an injective module. Yeah. And yeah. Shall we think about this? I mean, a way to see that Z over Z is not an injective module is that multiplication by 2 is an injective map, and you cannot extend the identity map from Z to Z along the multiplication by 2. This would be one example. And this one is Z module is the same as abelian groups, and Q is an example of a divisible abelian group, yeah, meaning that each element is an arbitrary sum of, should I say power? I can write every element A in Q as a sum of n times the same element, and I can do this for every n. And this divisibility is what helps in showing the injectivity of this module. Okay? But it's a concept that actually we will not use much in this course, I guess. The projectivity will be more important for this part, yeah? Even though the dual concept becomes relevant later when talks about cohomology, but right now we are still interested in homology. Okay, so next thing is we've discussed the exactness of the Hom-functor, and we've seen that it's actually equivalent to projectivity, and we've now introduced the dual concept of injectivity. So the game is now to repeat the process for the adjoint functor for the tensor product. So what happens there? And there, we just introduce a new notion to say what it means that the tensor product is exact. Namely, a left R module M is called flat if the tensor product with M turns out to be an exact functor. Okay, and there is again a proposition, this time saying that projective modules are flat. Yeah, and of course this concept of flat, it wouldn't have a different name if now the converse was also true. Yeah, so the converse is not true. Projective modules are flat, but there exist flat modules which are not projective. So in some sense, the situation is more complicated than one would anticipate. Yeah, it's sort of more difficult for the Hom-functor to be exact than it is for the Tensor-functor in this case, because the projective modules, the ones for which the Hom-functor are exact, they do also preserve exactness in the tensor product, but not the other way around. Yeah, so this is something sort of where the symmetry is broken. Okay, so how do we prove that projective modules are flat? So first of all, the easiest example of projective modules are free modules. And for free modules, it's pretty easy to see that they're flat. Because if we have a basis, meaning meaning M or F for free is of the form just the direct sum of a bunch of R's. So free modules, these ones are flat. Because, well, I mean, dually to what we did before, I mean, if we want to prove exactness of the tensor product functor, only preservation of injectivity is what one needs to prove, because in a short exact sequence, the 4 right terms, this is preserved, the exactness at that part. Only the injectivity, which is the exactness at the leftmost part of the short exact sequence, that's the one that needs additional consideration. And it does actually work for free modules, because if I have an injective, if I have a monomorphism F from N to M, and to this homomorphism I apply my functor tensor product with this free module F, then I can use a property of the tensor product. Yeah? Namely, if I just take the tensor product with such a free module, then what I get is just the product of as many, or I should say the direct sum of as many copies of the module as I had before summons of this R here. So in other words, I just get the direct sum over the index set I of a bunch of n's. And here I get the direct sum of a bunch of m's. And the morphism that this F here actually induces is just the diagonal one. Yeah, so it's just the direct sum of those, if you want. And, well, if it was injective and I only consider this diagonal homomorphism, then it is, of course, still injective. So injectivity is actually preserved for free modules. Yeah, so that works. And now we use, to get the general statement for projective modules, we use the characterization of projective modules as direct summons of free modules. So for a projective P, we just choose a complement which by this equivalent characterization of projectivity exists. So we take a complement Q such that the direct sum P plus Q is a free module. And in this case, I again have to apply my Tensor-functor to such a monomorphism F here. And what I get out of this is, the following. So I get n tensor P plus n tensor Q. So this is, yet another property of this, it's this distributivity property of the tensor product. If I take tensor product with this direct sum, then it's the same thing as I take the tensor product separately. There's no Q, no thing here. I take the tensor product separately, and afterwards I form the direct sum. Yeah, it's one of the properties of the tensor product. And this then goes to the same thing on the other side. So M tensor P plus M tensor Q. And, such a map here is actually injective if and only if, both these components map from here to here and here to here are injective. So if this is injective, I know this because it was a tensor product with a free module, but now I can conclude from this that also this portion from here to here is injective. So whence n tensor P to M tensor P, which is just this homomorphism F tensor P. This one is also injective. Okay, so projective modules are very convenient because they have nice convenient properties. They make both the Hom-functor and the Tensor-functor exact. And like I said, well, there are now flat modules which are not projective, so I should just give you an example to think about. So this is an example which already occurred earlier, namely the Z module Q is an example of a flat module. So it's flat, but it's not projective over Q. Did I say over Q? Over Z, I wanted to say, yeah? Q is flat, but not projective over Z. And, well, to see that it's not projective, one can use this divisibility property I alluded to earlier to see that actually homomorphisms from Q to some other mod, from Q to Z must be 0. And this cannot happen if Q was a direct summand of a free module. So this is a little exercise, but it's not too hard. So Q is actually flat, but not projective over Z. And finally, as another example of a module which is not flat, which we haven't seen so far, so let's do this. For each n at least 1, the Z module Z mod NZ, this torsion module, this one is not flat over Z. And this is so because I can just give you an injective homomorphism to which tensor product with Z mod NZ applied gives a non-injective homomorphism. And you can already guess which one this is going to be. Because this functor, blank tensor Z, Z mod NZ, turns the multiplication by n. So this is definitely an injective homomorphism. Yeah, I multiply every integral number by an integer n. And well, what happens if I apply the tensor product functor to both sides? Well, if I just take tensor product with Z over Z, that means I just get Z mod n on both sides here. So the induced map is the multiplication by n from Z mod NZ to itself. But that is, of course, the 0 homomorphism because n is 0 in Z mod n. So this turns this into Z mod NZ to Z mod NZ. Yeah, the 0 homomorphism from Z mod NZ to Z mod NZ is not injective if n is bigger than 1. Yeah? And it's actually the existence of these torsion elements which make this, or which affect this failure of flatness, and this will bring us to the next video about the Tor functor.